Okay, so today we will discuss about how the memories system, when I say it's not the one memory, different types of memories are being used when you build a computer. All these memories will contribute in its own way in building the computers. If you take a small embedded system like MP3 player, if you take MP3 player, now if somebody asks what types of memory it has got a variety of memories inside. It has got a RAM is there. The question is which type of RAM? It has RAM. It consists of the flash memory, which is called as E square PROM. Electrical erasable memory is there. It has got the battery backed up RAM, battery backed up RAM is there. So like this number of, and also it has got some SD card, so we can call as a flash disk or flash disk or SD card memory. That means that any system, small system you take it, it contains variety of memory types are present inside that. If you take a normal PC, a general purpose computer like a laptop or something, so it has got DRAMs, we call as a, so DDR, double data rate, SD RAMs, it has got, so it has got the cache memory, so which is nothing but SRAMs are there. So it has got, even in the cache memory, it has got L1 cache, L2 cache is there. So apart from that, it has got hard disk drive, or nowadays what is called as the flash disk also is available. SSDs, flash disk are also called as SSDs are also available. And it has got some booting program in the beginning, so it's called E square PROM. So it is also has got a battery backup RAM is there, secondary storage devices are there, magnetic disk is there, your CD-ROM optical disk is there. So that means that there is a number of types of memories are present inside a single computer. If you just ask the question, why can't we use one type of memory to design a computer or an embedded system? No, it's not possible at all, because varieties of memories are required because the purpose is different, the investment is different, the speed is different. So ultimately when we choose what type of memory is required, we should ask the purpose for what it is required. If you want a small memory to boot, to start your computer and load the operating system from the disk to the main memory, then you require a small E square PROM is required to hold that booting program. If I want to load my program and the data, I require a lot of main memory is required, and the cost should be less. So I'll go for what is called as, so DRAMs, I'll go for it. I want to increase the speed of my system performance, I'll go for some cache is required. I want to store a lot of programs, even I switch off the programs and my operating system should be there in my system, I'll go for an hard disk or a flash disk or SSD. So depends on the requirement, the different types of memories comes into picture. So that is why it's very crucial to understand all types of memories, how they're designed, what parameters to be considered, what are the benchmarks used. So when we are selecting the memories, all these concepts are required when we design any computer system. So as a computer science engineer, it's very crucial to identify the meaning, or identify the meaning of each type of memory and what parameters we have to look at for each type of memory, and how to design a system so which comprises of so many types of memory. So these are our requirements. So the next 1 hour or 45 minutes to 1 hour, we will study, go through the different type memories, how they are built, what benchmarks are used, so what is the way we have to select these memories, everything we will study now. Now when we say, when we start discussion to choose a particular memory, always the three important factors comes into picture. So one is the speed, we also call it an access time. So there are four metrics are generally used: access time, sometime memory cycle time we call as, then we also use a word called as latency. So we also use sometimes called as a bandwidth. That means that four metrics are very commonly used in the memories. So one is called an access time, which says that when I apply, as we have studied in the last class, when I apply the read signal to the memory, how much time does it take to place the data from the address location into the data bus? That's called an access time. We have seen when we return the timing diagram for the memory cycle study. So it took around 3 clock cycles. That somebody asked, what is an access time? I say 3 clock cycles. So what is a clock cycle? Clock cycle is nothing but 1 over the frequency or the speed at which the processor runs. If it's a 1 megahertz, it's a 1 microsecond. If 3 clock cycles are required, I can just say that 3 microsecond is the time required for placing the data from the address location onto the data bus. So 3 microsecond is my access time. But if somebody asks, tell me the total time required for the whole memory one cycle so that I can able to perform another memory cycle, read or write. So it is more than the access time. Maybe you can add another 1 or 2 clock cycles for that, 5 clock cycles, let's say 5 microsecond. So the cycle time is always more than the access time. So cycle time indicates how frequently or how fast I can able to perform one read operation to another read operation. It's a time you have to provide for one cycle memory read operation or write operation. It's called as a cycle time. Cycle time little more than the access time. So sometimes you use a word called latency. So latency is nothing but it's almost near to the cycle time. It says that, so how much time does it require to perform to one complete word read or write? The total time required to perform one memory word read or write is called as a latency, memory latency. So latency is a common term is used to compare many of the memories. Other time we also benchmark sometimes we use is a bandwidth. So bandwidth speaks about, because many times we read the memory not for a word, we read the memory for a block of data. So two types of readings will happen in the memory. One is the word reader write, or is a block reader write. Block is also sometimes we use a page. So page reader write. So whenever the page or the block is involved, it's not the one word, number of words we read at a time. So when we read it a number of words at a time, I cannot use an access time, cycle time, or a latency to measure the benchmark, to measure the that may not be the proper benchmark. So we use a bandwidth. Bandwidth talks about how many bits or bytes you are able to read per second. So bandwidth is nothing but number of bits or bytes we are able to read from the memory per second. It's a per second calculation. Whereas access time, cycle time, latency is what? It is a time. You can say 1 microsecond, 2 microsecond, 10 nanoseconds, like that. It's a time. Whereas the bandwidth is what? Per second measurement. So how do you measure a bandwidth? So generally the word length of a processor is also matters. If the word length is 32 bit, that means that whatever the amount of data per second you can read on single wire into the width of the data bus matters into picture. So bandwidth is a product of what? Number of bits I can read per second on one single wire into the width of the data bus. That will be the bandwidth. So these are the 4 parameters which are generally used as a benchmarking for comparing the memories. So always, so access to all these times, that means that the bandwidth should be the more, whereas these things should be always what? Less. So whenever you purchase any memory, the lesser the latency, the lesser the access time, it's a better, because you can able to do more number of operations per second. The bandwidth should always be more, because why? You can able to, the bulk of data you can transfer within a given time. So the next parameter is called as the size. The size is another important parameter when we select number of memories. For example, size depends upon how each cell of the memory is manufactured. So we'll be learning after this concept how each cell is manufactured. If in the manufacturing, if it's one transistor is involved in manufacturing of a one cell, some space is required. If the same cell is manufactured using a 5 transistors, space is 5 times is more. That is why, so as we study further now, the SRAMs will take more space, DRAMs will take less space. So that means that size is a crucial factor. When you're providing large amount of memory in these today's laptops, so you cannot, there is no affordability to increase the size of your laptop just because of the memory. So size is also crucial. So what is the challenge is reduce the size and increase the capacity of this one. So size and also the total cost. So cost is also important factor. So the speed should be higher speed memory is required. That is access time should be less. Size it takes for a large quantity of memory should be always the less, and the cost should be always what? The less. So when we purchase any memories, if I'm able to get number of bits per a given rupee. So if, for example, if I am going to 1 gigabyte, I'm going to purchase memory, how much of less investment I can make on that? It's a very crucial factor. So speed, size, cost are all matters in case of memory. Another important thing we should assume is we want the large memory, the large size memory, the large capacity of memory is required. The more the memory, it's always a better. There is no satisfaction from the from the human being point of view. Because why? The more the memory is there, more programs you can able to keep in the memory so that multitasking is possible. You feel there is no lag in your execution of your programs. So the more the capacity you require, what is the challenge? So the limited number of address lanes, or even though the processor has the address lanes, let's say it has got a 64 address line, 2 to the 64. So large quantity of memory is possible, but only thing is physically can you able to place that much of memory in a computer? Do I have a space for that? And do I have a money for that? That also comes into picture. So these are the few of the factors we have to consider whenever we want to purchase the memory. Now we'll get into the details about these memories. Now, so before we will identify the what types of memories, what is a hierarchy, what is the first memory you have to place it, what is the second memory, like that, we will general classification of memories we will get into this one. Now, so we will target about first the main memory, what are the main memory types are available. So then we will just mention what are the secondary memories are there. We are not getting into details of the secondary memory. We know that any memory which is connected directly to the processor address bus, that means that the processor address bus is used to access your memory, that memory is called as a main memory. So anything which is not connected to the processor address bus, that means that whenever the processor generates address, it's not directly mapped to that memory location, then that means it's called as secondary memory. So secondary memories, we know that you have the magnetic disk is there, you have magnetic tapes are there, you have optical disk is there. So nowadays we call as an SSD, a flash drives, a flash disk are there. These are all the types of secondary memory. So the very challenging to design and understand is the main memory. So what are the types of main memories will be available? Almost all the main memories we can classify into two types. The memories which are volatile, the memories which are not volatile. So RAM is characterized by what is called as volatile. It's a volatile in the sense. So whenever the power is given, the data will be there. As soon as the power is removed, the data also goes. When the power comes, data will be there in the RAM. In the memory bits, always flip-flops also. When the power is lost, flip-flop data will go. When the power comes, some data will be there flip-flop, but it's a not a valid data. Some random data comes into the flip-flop, as we have seen in the lab experiments. So similarly, read-only memory is non-volatile in the sense whatever the program stored in this memory will be there even the power is lost. Both of these memories will have a same characteristic called as a random. So I can use it. So even though it's a read-only memory, so there is a property called as random access property is there in both the cases. What do you mean by this property for both of them? That means that compared to the secondary memory and the main memory, the time it takes for reading or writing any word in a memory is always the same. It's a fixed set. If there are 1,000 words are there in the memory, the time it takes to read and write the first word, that is the word located at address 0, is same as the time it takes to read and write the word 1,000 also. The same rule is not applicable for a magnetic disk. If you are reading the tracks which are near to the head, the time it takes is what? Faster. If you're reading the data which is located in the farther tracks of the magnetic disk, it takes a more time. That means that in secondary memory, the time it takes for reading the data depends upon the position of the data on the disk. Whereas the main memory, which is being built using a semiconductor integrated technology, the time it takes for reading any word, the time it takes to write any word is always a fixed. So that means that it's also called as random access memory. You can randomly access any of the location with the same time. So this property is present both in case of a RAM also and the ROM also, because both places we use semiconductor integrated technology. Only thing is difference between ROM and RAM is one is volatile, other is a non-volatile. In the RAM, there are two technologies are present. So these two technologies is based only on the cost and the space. The one is called SRAM. So here the features of the SRAM is what? Its speed is very high speed. If at all, if somebody asks, tell me the memory which is highest speed, is always the SRAM. Of course, registers are always the highest speed, but we don't know. I'm not consider that register as a part of the main memory, because registers are part of the processor itself. As we studied in the last class yesterday, registers are present inside the CPU itself. So we don't consider as a memory. Of course, in the hierarchy, we write the registers, but we always consider registers as a part of the CPU itself. So any other thing which you are placing apart from the CPU, we consider as a main memory. So in main memory, generally, if somebody asks, what is this memory which is of highest speed? SRAM is an highest speed, and it takes more space compared to the other types of RAM. So more space it takes, and the cost is more. Why? Because we will be knowing in the construction it requires more number of transistors. So to reduce the cost and to have large number of memory cells in a given space, high density, to increase the density, DRAMs are used. So DRAMs are popular for high density of the memory. That means that more number of memory cells you can put in the given area, and the cost is less. It is cheaper. DRAMs are cheaper, but it has got its own constraints. We will study them in details. In SRAMs also, there are two types of memories are there. If the RAMs works in synchronization with the CPU clock, we know that there is one master clock is there which coordinates all the operations inside the processor. We studied yesterday. Same clock if used to synchronize the operations of read and write inside the RAM. So that is called a synchronous RAM. If it is not synchronized with the clock, so there is a separate memory controller used which generates the related control signal. Then we call as an asynchronous RAM. So it's a synchronous RAM. Synchronous SRAMs is one. So other is called as asynchronous SRAMs. So nowadays most of the RAMs what is used in the motherboards or in the embedded system are synchronous type only. In synchronous, there's a next category is there which is improved on that, which is a double data rate, DDR SDRAMs. So which is faster than the normal SRAM. It is all the concepts the same thing, is only in the clock cycle. In generally, normally clock, if we take one clock cycle, one data transfer will take place. That means one edge, either the positive or negative edge used to for the data transfer. If I'm able to transfer in a given clock cycle, both for the positive edge and the negative edge data is transferred, then it's called as a double data transfer. So that is called as DDR SDRAMs are used. So these DDR RAMs are used to prepare what is called memory modules. They put 16, 32 such chips in one memory PCB, and these chips are placed here 32, and these modules are used in the computer. Whenever you look at the motherboard, there is a space will be given for memory modules. So these are the places where the memory modules are inserted. These are generally they use DDR SDRAMs. Now latest other technologies have come which has been performance little better than the DDR RAMs also available now. So these are the types of RAMs what is available. Similarly, if you go to the if you these so there is a one this asynchronous, I'm just putting there's a one change is here. These are all part of DRAMs. It's not SRAMs are standard. These are all asynchronous DRAM. So synchronous it's a DRAM. So DDR, so synchronous DRAMs. So there's one change. I'm just marking it here. Whatever the two types of RAMs are specified, one is called as asynchronous and synchronous. They comes under the DRAM. It is not under the SRAM. So SRAMs are standard. SRAMs is only one type is there. So SRAMs are generally used to build cache memories. SRAMs are used generally to build cache memories. So DRAMs are used to build the main memory of the PCs, main memory of personal computers and the laptops. So just make a note here. So this is not the part of it. So the both asynchronous and the synchronous DRAMs are a type of DRAMs. So they are not the type of SRAMs. So SRAMs are standard type. So these are very limited usage. They will do it because it's very costly. Very costly. They're made up of the flip-flops. Since 5 transistors required for one flip-flop, so they're very costly. They'll be used generally implement the cached memory. So now, so these are what are the types of the RAMs available. SRAM and DRAM types are available. Now we'll see what are the types of ROMs are available. So ROM, as from the factory, if you purchase the ROM chip, it is used for storing the program one time. That means that at the time of manufacturing itself, if the manufacturer writes the program and gives the ROM chip, we call it as a read-only memory, ROM itself. When I say programmable read-only memory, at one shot, one time, I can able to write my program of my choice into the read-only memory. Either we can send that program to the manufacturer and he can do it, or at the factory itself, or at the once you get the chips, you can also do it. It's called programmable read-only memory. One time you can able to program it. Many times what will happen when the product development is happening, many times you're supposed to write and read it until you finish the project development. So in such cases we is called as EEPROM. So EEPROMs are also called as erasable programmable RAMs. Earlier days they use what is called as a technology called as ultraviolet. Ultraviolet means, so in these memory chips there is a small glass window will be there. Through this glass window the contents of the memory will be erased using ultraviolet rays. That means that physically you have to remove the chip from the board where the EEPROM is there, take that chip to the ultraviolet UV eraser, place into the UV eraser and just keep it there for 10 minutes, then the contents will be lost. Then you have to bring that back and you have to connect to your modules, or there's a EEPROM programmer is there, through that you have to program it. So earlier days we were paying 30 rupees, 40 rupees for every time. Every time we change anything in the code, so we should be very careful. If when you develop a program, if something mistake is there, you have to remember 30 rupees is gone. Again, we have to go to the place where that eraser is there, erase it and get it program, you have to come back. So where do we use EEPROMs? Generally, when you build any embedded system, for example, like an Arduino board, earlier days when there was no Arduino board was there, the microcontrollers will have what is called EEPROM will be there. There, the program was fused. So every time there's a change in the microcontroller program or embedded system, you have to rewrite into the EEPROM. So after this, there's a new technology is developed called as E-square PROM, electrically erasable PROM. So here what happened is that is you don't require to remove the chip from the board, and then you don't require ultraviolet rays. On the board itself, you can able to erase the contents of that the memory, read-only memory, and you can able to write the program. Only thing is some extra voltages are there. What is called programming voltages is required. That means that normal voltages are 5 volts or 3.2 volts. Here it requires extra programming voltage, 18 volt, 12 volts, some extra higher programming voltage required to burn the contents of the cells instead of ultraviolet rays. So this was commonly used in the other days. So after this, now, so very recently, instead of E-square PROMs, there's what is called flash memories available. So flash memories are available now. So flash memory is nothing but you don't require a separate programming voltage, also not required. The flash memory chips that which is used in your pen drives, in your SD card, which you can able to read and write without a programming voltage. But the only disadvantage is you can read any location simultaneously whichever you require randomly, but when you want to write the whole page, you have to write it. You cannot write a single word in a flash in SD cards or a flash memory chips. You cannot just write into one particular byte or a word. You have to write the whole page. Then what we have to do, first we have to erase the whole page and then write into the page. So we have to read the page, modify whatever required into a buffer, and then erase, and then you have to write it. So this is the one disadvantage, the flash memory. But flash memory is more suitable because you don't require extra separate programming voltage required. Normal 3.3 voltage is sufficient. So the most of the memories, ROM type memory which is currently used in the market, are flash memories. If you take any microcontroller, let's say you take our microcontroller LPC2148, which you are studying in the next semester. So this has got a inside a memory called, it's got a read-only memory. What type of memory used? They use a flash 512 kilobytes has been used. So that means that using normal computer, you can just connect your USB cable and you can program it. You can take an Arduino board. Arduino board has got some memory inside. What memory it has got inside the microcontroller which is used in Arduino board? It's an E-square. It's a flash memory. It's a type of ROM. So where without giving any extra thing, just a USB pen drive is good enough. USB cable is good enough to program that one. So all the memories what used in the embedded systems, all the memories used in the SD card and the pen drive, they're all of the types called as flash memories nowadays. Only thing, the reading is possible, writing at a page is you to done it, but you need not worry about this because this taken care from the low level. Drivers will take care of it. When you are writing, developing a drivers at the low level, then you should know that how to write it, what is the page, how to read an address and all those things. It's a very interesting to write a driver for a flash memory chip. So these are the types of the read-only memories what is available in the market. Now we have seen that all types of memories what is available in the market and what are used inside a computer. So in the RAM there is also one category is there. So that is nothing but it's an SRAM. Only thing is we people call it a battery backup RAM. So battery backed up RAM. It is nothing but a RAM only. It's nothing but a normal RAM only. But only thing is there's a small batteries associated with the memory. Sometimes it may be inside present. It works for 10 years. Sometimes the battery is present outside. So as soon as the power is switched off, the contents of the RAM will not disappear. It will be there itself. So why it's required? For example, date, time, some passwords. These are the information which we don't want to disappear. So even the switch off, it should be there. But at the same time, you're supposed to modify that at the runtime. I cannot use a ROM for this one because ROM means it's a fixed one-time program. I have to do it. It's not possible ROM. So can it be? It's a part of the motherboard itself. It's a part of the same board itself where there is no secondary storage will be available. When sometimes you take a motherboard, there is no secondary storage available. If you take a embedded system board, there is no secondary storage available. So you should be placed sometime in some place in the board itself. I cannot store in the RAM. I cannot store in the ROM. So that provide a battery backup. RAM is available. So these are the different types of memories. What is present in any embedded system or a normal computer? Am I audible? I'm audible. Hello.
Sir, audible, sir. Yes,
Oh.
sir.
Now we will go to the different types of memory design. So before we will go to the different types of memory design, we will just see that how a memory chip is organized. If you purchase a memory chip, what will be there inside a memory chip? We'll see one case, one example. So let's design. Let's find out how 128-bit memory chip is designed inside 128-bit memory. So when you purchase any memory chip, so in the market, so you should identify immediately. I have just taken very small size only for theoretical point of view. You don't get 128-bit, you get 2 megabits, so 64 kilobit like that. I'm just for understanding point of view, I've taken a small size. So any memory chip you purchase in the market, the first thing you have to ask is what is the size of the chip. Generally, it is they're telling the chip in terms of bits, 64 kilobits, 64 megabits, 128 bits like that. Now the chip whatever I have taken is now 128-bit chip. Now the first question I have answered is what is the size of my chip. The first question I have answered is what is the size of this chip. The second question I supposed to answer is what is an organization of this memory. This memory is organized into rows and columns. How many rows are present, how many columns are present, that decides how many addresses are required for this chip, how many data lines are required for this chip. So let's take in this case it is organized into, so let's say 16 rows into 8. So 16 rows into 8. So if you multiply 16 into 8, so I am going to get 128 bits. Now, so like this, any chip we give now onwards, you purchase from the market, first you have to ask what is the size of the memory in terms of bits, then how it is organized inside. The same 128 bits can organize in a different way. It can be 32 rows and number of columns in a row can be different. It can be it can be 64 rows and the number of columns can be less. It can be 128 rows and each column can be 1. Like that, variety of combinations will come. That is why you have to purchase multiple memory chips to prepare one memory requirement. So if I am building a computer with 1 mega into 32, that means that I may require 1 mega 1-bit chips of 32 bits. 32 chips may be requiring. That means that, so you have to choose the multiple memory chips to design a given memory requirement. So now let's see what will be there inside. Any memory chip, what does it has got? Now I said it's a 16 rows are there. So I'll be writing, let's say 16 rows will be there. We will call each row as the word we call as, because why we call as a word, it's called as a, so word line, we use a word called as a word line in the further description. So word line 0, word line 1, it's a word line 15. Because why? Memory is organized as the rows and column. Each row is considered as what? One word. Each row contributes one word of data. Now, there are 8 columns there, so that I'll be writing 8. Each of these columns will contribute one bit. Let's say it's a bit 0, so then bit 7, bit 6, let's say. So that means that these will contribute 8 bits for me, and these are, there are 16 words are there, 16 words or word locations, or 16 rows are available here. Now, at the intersection of every row and column, one memory cell will be available. So, since we are designing a RAM, so a RAM, one bit of memory will be prepared by one flip-flop or a latch. Every flip-flop and a latch will have two bits will be available. One is called Q, other is called Q bar. So Q and Q bar are complementary outputs. So those Q and Q bar are used to access the data of the memory. So we generally called as what? The two complement bits will be available. So we call it, for example, if the B7, we call as B7 complement bit Q bar. So this is a B7, the normal bit Q bit is available. So these data, what is available at every column, are short together. For example, this short together, they short together, and this data is available to a type of circuit which is required to read the data present in a particular bit of a word. It is also, the circuit is useful to write the required data into a particular cell. So we require a circuit which we can read the data present in a given bit. It's called a sense circuit. We have a set of transistors, or a set of transistors and related circuits required to write the data into the given bit. That's called write. So sense write circuit is present at every bit of the memory. This the requirement of this is what? It has the capability to perform the reading or writing. That is why these sense and write circuits will require what is called as a signal called read and write bar, which is generated by the processor. And also, since multiple chips are present inside a computer system, it's not the one chip, so many chips are there. There's also called a chip select will be there. So these are the two signals which are connected to sense and write circuit. So these circuits are present everywhere. Now the data, whatever the data bits which are connected to the computer, that is to the processor data bus, so will be two directional. I can write into this, I can read from this one. That is why, so we will write like this. It is nothing but one is reading, one is for reading, and then the lines comes like this. So this one. So now I have understood that to design any memory chip, we require sense and write circuit for every column bit. So all the columns of the words are shorted together and provide what is called as one bit of data. So now we have understood how columns are together. At a time, I'm able to select only one word at a time. Even though 16 words are there, I can read only what? One word, one location I can able to read it. That is why all the cells which are present in a given row or a word are short together. They will be short together. There is what is called one enable pin will be there for every cell. So that is called as the word 0. So that means that this word line 0 is connected to what? One control pin or enable pin of all the cells in that row. Similarly, the 1. So 1 is connected to what? All the enable pins of the in the cell. Similarly, the word 15. So it controls the enable of all the cells. So any one of the word, I'll be selecting it based on the address what is being supplied by the user, by the processor. Now, if I supply the address, let's say now how many addresses are there? 16 addresses are there. So 16 addresses means I require 4 address lines are there. So I'll require 4 address lines are required. So one moment. So I require 4 address lines are there. So they're called as A3, A2, A1, A0. 4 address lines are required. These 4 address lines 2 to the power of 4, 16 combinations are there. That means that when the processor generates an address, you should have some circuit inside the memory which will take the 4 address lines, convert into 16 word select signals are there. That is why every memory chip has got inbuilt a decoder is there. Now what is the size of the decoder? 4 to 16 decoder. This decoder is the one which select all the word enable lines there. That is why always if somebody asks what is the use of a decoder, one of the applications of the decoder is what? Decoders are used to design the memory chips. Without the decoder, you cannot design the memory chips. So you have to take the encoded address information, what is available in the address lines, decode them, and select one of the rows or one of the words of the memory chip. Once you select one of the word, the contents what is present in the cells present in that word will be read or will be written using the sense and write circuit with the help of read write bar and the CS lines. This is how the memories are organized. Now if somebody asks totally how many pins are there in this particular chip, how many pins are there, we can immediately say 4 address lines are there for this one, plus 8 data lines are there for this chip. So similarly, we have 2 lines are there, one for the read write bar, other is the chip select, 2 for the power supply. So one for the VCC, other for the ground. So totally now together, so 4, 12, so 14 and 16. So I can just say 16 pins. Any memory chip you take it, even if they tell the size, they tell the organization, you can calculate the number of pins are required for the chip. It's so easily you can able to find out how many pins are there, what those pins for given any memory chip, if you know these fundamental concepts. Now we have understood that how the memory is organized in any memory chip. Memory is not always organized this method. Memory is organized in different way also. So sometimes they use a multiplexer also inside the memory also. Let's see one such small thing quickly. So I will use another memory organization. It is a completely different case. Now let's say I will take a memory chip of 1 kilobit. 1 kilobit memory I will take it. So I know the size now. First question is what is the size? 1 kilo, I know that. The next question I'm supposed to ask is what is an organization of this memory? So let's say organization of this memory is different. So the organization of the memory depends upon the manufacturer for what requirement is manufactured it. Now we have considered a little larger size memory compared to the previous. Previous was only 120 bits are there. Now 1 kilo, 1024 bits I have taken it. So this circuit, we will assume that it is organized into 128 into 8. See, in the previous case, it is 16 into 8. Now 1 kilobit is organized into 128 into 8 memory. So now if this is a different one. This is let's take the other organization now. So this one, whatever the memory I have taken, it depends upon the size we will able to organize this one. So this case, it's easy to understand. We'll take a little bigger size now. Let's say I will take a larger size, this one. I'll take 4 mega bit chip. I'll take it. So this we can guess is easily. So I'll take it looks like the previous one. I'll take the bigger one. 4 megabit chip I'll take it, which is commercially available. The organization of this chip is 512 kilo into 8. We know that 2 into 512k means 1024k. So that is so it will be, if I say 512k into 8, so 4 megabit I'm going to get it. So now this is the organization. In this case, 512k into 8 means how many address lines are required? Because the 512 into 1024, that is the number of rows are present for that. We know that 2 to the power of 20 is 1 mega. 2 to the power of 19 is what? 512k. That means that 19 address lines are required to access the 512 into 1024, the rows. We require it. And how many data lines are they required for the chip? 8 data lines are required. So now we know that 19 address lines are required, 8 data lines are required for this chip. How this chip is organized? This chip is organized little different way. So little different way. So I wanted to give this tip because always organizations are not in the same way. It will be different. Sometimes you require a multiplexer also. Now among the the address lines whatever available here, so the capacity which you are addressing, the address lines also increases. So based on these requirements, we are able to design the chips. Sometimes what will happen is, so the cells inside are organized into 32 into by 32. Then again, in one word, you have number of bits or more. Then I have to select one byte among the words. So that concept is also available in some of the chips. So what I mean is, for example, if this is an array, I may have, let's say, number of rows available here. Some set of rows are there, and each row number of columns are provided. These number of columns need not be 8. So let's say it can be 32. So inside if it's a 32, but at a time I'll be requiring what? Only 8 will be required. In such cases, So a multiplexer will be used in the circuit. First a row will be selected. In that row the number of bits will be not 8, it will be more than the 8. Say let's say it's 32 is available, but my data bus is only 8 bits. So I will be select 1 byte among the 32. That means that a multiplexers will be used. So sometimes along with the decoders, the output multiplexer, the multiplexer which generates so 32 to a particular a bit, a particular byte, and also a demultiplexer used when you want to write 1 byte to a particular locations. So this also concept is used in some of the memory chips. So now we will go to the study the static memories, how the static memories are built. Now, so static memories are basically are built using a basic what is called as one bit of memory cells. One bit of memory cell is being designed using what is called as the latch or a flip-flop we call as. So let's understand how a memory cell of 1 bit size is implemented in a static memory. We know that a bistable latch like this is the basis for any storage. We have studied this when we built flip-flops, latches, everything. This type of arrangement is capable of storing 1 bit of information even when the data is removed from the inputs. If this contains 1 and this contains 0, this state will be held in this bistable latch till the power is applied. Even though inputs is removed, so if you drive through the inputs to the new state 0 and 1, even though you remove the inputs, still it holds the data. This is a principle behind holding 1 bit of information in any static memory. Now, how this circuit is designed? So let's say this circuit is designed so with a particular inverter. I'll just making an arrangement, rearrangement of this one. So now I am making little rearrangement of this one. I've just made a rearrangement of these transistors. Now I connected output to the input, input to the output. I just made an arrangement. Now only when required the cell has to be enabled. If not required, the cell is not to be enabled. We know that the word line, whatever is generated by the decoder, will select a particular word. When it selects a particular word, a particular cell in that word is also get selected. So for that, to enable or disable the cell, so the two transistors are present. So at both the outputs, there is a complemented output and the uncomplemented output, the Q and Q bar. So they have connected. These are the CMOS transistors. So now I'll call this transistor as a T1, this transistor as a T2. So now this one is a line, so which is called as, let's say, complement line. We say B bar. This is uncomplemented line. I'm calling as the B line. Now, so these transistor bases together, they shorted together, and they call as the word line. They call as the word line. So this word line connects to all the cells present in a given word. Now, how does a transistor works? Whenever the transistor is supplied with a logic 1, the transistor acts like a short. That means that gate which is open, it gets connected here. Then whatever the data present inside, whatever the data present at the output of this inverters will be available at the B and the B bar pin. So whenever you supply the 0 to this one, the transistor gets open. Then what will happen? Whatever the data present in the bistable latch will be held with the principle. We know that when it's not connected, the data will be available there because the power is there. It will be held. This is the principle how it is connected. It's enabled when required and it's not enabled when it's not required for reading. So now how this particular, now we'll go a little more in detail, how this particular inverter or a what is called as a one gate is being built in particularly in the semiconductor integrated technology. There is a number of families there, TTL, CMOS, like that. CMOS is a popular technology used for manufacturing these memory cells. Now, each of this inverter is built using two transistors. Now, what I will do is I am building the whole of this circuit. I am building the whole of this circuit now with how exactly it is manufactured inside. Every inverter can be manufactured by using two transistors. So I will take two transistors. Now two transistors. I will build one inverter. How do you build one inverter? So always these transistors, whatever I have taken, two transistors, I'll call them as so T3. So I'll be using one more here, that is a T4. So I'll be calling this as a, let's say, T5. I'll be writing here one more, T6. So now I'll be calling this as a T3 and T5 transistors. T3 and T5 transistors are used to build one inverter. Now, always these inverters should be connected. These transistor gates should be connected such that when one is open, other should be closed. When one is closed, other should be open. That is why it's a bubble is available. We write like this. The base, I'll connect it. So this will be the one base. It's available here now. It's shorted. Similarly, the drain of the transistor are connected to the power supply. So it's connected to the power supply. So it's a VDD, drain power supply is connected. It is 3.3 volts or it can be 5 volts. In an older system it's a 5 volts. Nowadays it's a 3.3 voltage. Now other point, that's a source, is grounded. It's a ground. Now so this is the input. Now the other 2 points which are available for the transistor, will be shorting them together, and which gives the output. Now what is an output? Let's say in this case, let's say this is a one output X, this is another output Y. Now I'll write this as a X. Now I have prepared one inverter. How does it work? If the transistor T5 is on, T5, that means it's shorted, you will get this whole of this value, that is X will be grounded. You will get a 0 here. So whenever the T5 is open, that means that T3 is on, then what will happen? X is connected to the VDD and you are going to get a 1. Always this inverter works like this. It depends upon the what input you are providing here. Either since we are using a bubble, whatever the data we give it here, either T3 is on or T5 is on, any one of these on. Based on which transistor is on, either we will be getting a 0 or 1. So now we will write another inverter. Now I'll be writing another inverter. So one more inverter, I'll be writing it. Again, I'll be putting in opposite configuration. So T6, I will write this as another transistor. Both of them I'll short together. This I'll short together, and it becomes the Y. And output of this I connect to here, and the source I'll be connecting to the ground. So now again this is a common point. Now we know that output of one should be connected to the input of the one should be connected to the output. Now what I will do is, so whatever the value I have here should be connected to the other one, should be connected to the output of this one. So I'll take this one, I will connect this to the here, that is why I'll make a connection here. Similarly, I take the X, I will connect this value of the X to the shorted point, that is I'll connect to here. Now I made a connection. This is the connection 1 point. So this is another connection I made them, that is it's connected here. Now I have connected output of one to the input of the other one. Again, the output of one I just connected to what? Input of the another one I connected. Now I made all the connections what is required for this one. Now how does the overall circuit will work? Now, so for example, if the X is, if the two conditions are there, if the X is, let's say 0 and Y is, let's say Y is so 1, this condition, that means the output. If the X is 0 means, that is T5 is on, so T3 is off. Similarly, so since the Y is equal to 1, the T4 is on and the T6 is off. Like this, we can able to find out what is the value for each of this one. We can able to find out. I think we can rewrite one more time, since it's, I think I just moved the paper. So like this, we can able to find out. If for example, if X is equal to 1, Y is equal to 0, it's an opposite condition. So T5 is equal to off. So T3 is equal to on. So similarly, so T4 is equal to off and T6 is equal to on. So like that, we can able to identify, that mean that this particular configuration of transistors can be used. Now, apart from this, you have one more transistor here, which is connected already available, that is a T1, which is similar to this, and one more transistor which is similar to this is connected to here. So totally 4 plus 2. So totally how many transistors we have? Totally I have totally 6 transistors are required to design one memory cell. So now, if somebody says that if I want to implement one bit of memory, if I want to implement one bit of memory of SRAM, so I require a space for 6 transistors are required. 6 transistors are required. So that is why the every one bit of SRAM is very costly and it requires more space is required because the space consumption is very high because 6 transistors you have to accommodate. But one of the properties of CMOS which has been used to design the circuit is what? Low power consumption. Low power consumption. And since we have used flip-flops or the latches has been used for the technology, it's in high speed. So if somebody asks SRAM, what are the features of that? These are the features. Since it is made up of flip-flops, flip-flops work at the speed of the process, at the speed of the processor speed, they are able to supply the data within a single clock cycle. You can complete the operation in a single clock cycle. You can bring in the data from the memory and put into the register. Since flip-flops are used, the speed of the memory cell is very high speed. Since the CMOS technology used, we have seen in the previous circuit, always what will happen whenever the cell is not selected, the T1 transistor is off, the T2 transistor is off, and we have seen that each inverter, one of the transistors is always off. There is no active path between the power supply VD to the ground when the cell is not selected. When the word line is not selected, there is no path for the power to pass from VD to this VD2 to VSS. There is a ground. That means that power consumption is very less in a CMOS circuit. So this is an advantage, the low power consumption. Only thing is the disadvantage, it's costly and it requires more space because of the 6 transistors. To overcome this, the what is called as DRAMs are introduced into the market. So what are the DRAMs? So DRAMs are a special technology which is being used. So which provides or which requires less space to manufacture one bit of a cell. How it is possible? So we know that unless we organize anything like this, that is make the output connect like this configuration is not there, you cannot store one bit of information. This is the greatest invention. Why it's called the greatest invention? This arrangement has a capability to store one bit of information even if the inputs are remote. Now I don't work because 4 transistors are required here, 4 plus another 2 for enabling or disabling. So 8 transistors required. At least I assume that inverters 4 transistors required. Now I don't want to use 4 transistors, but I want to store one bit of information. How it is possible? Yes, there is an element, there is a component in electronics which is known from the decay, from the centuries, which can store the charge what is being present in that component. So that is called as capacitor. The whole concept of DRAMs is what? Capacitor is a fundamental element which is used to hold the voltage or the charge which is being present in the capacitor. So this facility of holding on to certain voltage 1 or 0 is a fundamental principle behind the DRAM. But when do you charge that one? When do you release that one? Again you require some component which enables this charging or disabling. That is nothing but again a transistor. So one transistor has been used here. So again, the CMOS transistor is used. So this CMOS transistor, the base is controlled by the word line. The word line, that means that all the cells present in a word are enabled or disabled through this word line. So the one of the transistor end is connected to the capacitor, other end is connected to the bit line which carries the data. This bit line is connected to the sense and write circuit. Sense and write circuit, they are connected. Sense and write circuit, they are connected. Now, so whenever you want to write 1 to this one, the transistor is enabled and the 1 is applied here, then what will happen? It gets charged 1. So now what will happen? The plus 5 volts or 3.3 volts remain in this charge, remain in this capacitor. If I want to store the 0, apply the 0, then it will be charged to what? Instead of this one, it will be charged to 0 voltage. So capacitor contains the logic 1 or 0 information. but it's very good. So you require only one transistor, the space required is very less and the cost is also less, because instead of investment is 1:4, 4 transistors required, so divide by 4. So if the 100 rupees is required there, only 25 rupees is sufficient to design one DRAM cell. But what is the disadvantage here? What are the challenges here? The challenge is the capacitor has got an inherent property that after you charge for the 5 volts, if you leave like that, it, even though the transistor is disabled, transistor is disconnected from the circuit, it is able to discharge that one. You may ask a question, how it can discharge when the transistor is open? So all of the capacitors has got what is called some leakage resistance will be there, parallel to that leakage resistance will be there, some resistance will be there. So some leakage resistance will be there. Through that it can able to discharge, or even though transistor is off, there is small picoamperes current will be drawn from the transistor also, even when the switch off also. So these are the two places where it will discharge. So after some time, let's say 60 millisecond, 30 millisecond, the data inside which was there plus 5 volts, it keeps on reduces, it becomes plus 4 volts, it becomes 3.3 voltage, at sometimes it becomes 2 voltage, 2 volt. When it reaches 2 volts, that means that it's not considered as 1. Anything above 2.8 volts to 5 volts we consider as a logic 1. When it reaches below 2 voltage, that means that it's changing the state from 1 to 0. So that it is not, it's losing that one. So what should we do it? So only way to avoid this discharge is we use a concept called refreshing of the DRAM cells. So what is a refreshing? That means within a particular time, let's say in the modern day SDRAMs, they support around 64 milliseconds. That means within 64 milliseconds, if you allow 64 milliseconds, if you charge the capacitor and don't use for 64 milliseconds, the contents will be lost, in the sense 1 becomes 0. So before 64 milliseconds completes, sometime you read the value of what is the capacitor, recharge it. If it's a 1, you make it 1. If it's 0, you make it 0. Where is that intelligence? That intelligence is built in the sense and write circuit. So sense and write circuit has got the capacity. It just read what is the value present in the capacitor. So if it is above 2.8 volts, that above the threshold value, it recharges to 1. If it is below the threshold value, that means it's 0, it recharges to 0. So this facility should be there in any of the DRAM chips. But what are the advantages of DRAMs? So it is cheaper because only one transistor is good enough to design the circuit. What is a space? It requires very less space. That means that very high density you can achieve in the memories because of only one transistor is required. So cheaper in space. So what is the challenge? It is a slower compared to your SRAMs, because this requires what is called as refreshing. So if let's say it works at 100 nanosecond, SRAMs works at a 10 nanoseconds. If 4 clock cycles are required for a DRAM, 1 clock cycle is good enough for the SRAMs. So these are the advantages and disadvantages of SRAMs and the DRAMs. So now we have understood that how DRAMs are designed. So there are two types of DRAMs are available which are commonly used in the market. So the first DRAM is called as asynchronous DRAMs, asynchronous DRAMs, asynchronous asynchronous DRAMs, asynchronous DRAMs. Now, how does asynchronous DRAMs are built? Now, so the concepts what I'm going to now explain is applicable for both asynchronous and synchronous DRAMs only. There's only one difference is one is synchronous with the CPU clock, other is not synchronous with the CPU clock. But there are certain new technologies is being used in case of these DRAMs. So let us understand now how these asynchronous DRAMs are built. What are the concepts are used? We will learn that using one chip itself. So we will take 116 megabit DRAM chip. I'll take it now. I'll explain that how it is organized, so that a lot of concepts you can learn how DRAMs are available. Now, this DRAM chip, that is a 16 megabit DRAM chip, it is organized. The cells are organized in the form of 4K into 4K. You can multiply 4K means what? 4096 into 4096 multiply, you'll get a 16 megabits. So they are organized like this. So that means that I will write a cell inside the DRAM. They are organized like this. So the number of rows what is present is how many? 4096 rows are there. Again there are 4096 columns are there. 4096 columns are there. Now these columns, so they are providing the total size of the bus. The chip is providing 8-bit bus they are providing. D7 to 0 they provide. That means that at a time I can able to read 8 bits. That is why they have grouped 4096 columns into what is called as 512 into 8. If you multiply 512 into 8, you are going to get 4096. That means that in every column there are 512 bytes are available. 512 bytes are there. Any one byte of the given row, I'll be selecting it and I'll be passing that to this one here. Now, so these 512, the bytes or 4096 columns which are organized into 512 bytes are available to a circuit called, as we have mentioned in the previously, to the sense and write circuits. These are the circuits which gives that one. Now, so sense and write circuits will be fed with all the 512 into 8, 4096 columns that come to here. Now we will see that what are the other logics required. Now to select one among the 4096 row, I require a circuit which we already learned in SRAM. It's called as decoder. So I am calling as a row decoder because it's used to select one particular row. Now how many rows are there? 4096 rows are there. Now, so the total number of rows, the 4096 is there, which requires how many address lines? So for example, if I take 2 to the power of 10, it is 1k. 2 to the power of 11, it is 2k. So 2 to the power of 12, it's a 4k. That means that, so 12 is a 4k. That is 12 address lines are required. So 12 means, so totally 12 address lines are required to generate a row address. Now I have to supply the 12 address lines here now. Similarly, after selecting the 12, sending the 12 address lines, I'll be selecting one of the row. Now, in each row, you have totally 512 sets of bytes are there. 512 bytes are there. I have to select one among the 512. So for that, whatever the data we are getting from the sense and write circuit, I have to give the data to a column decoder because I have to select one column. So one column is made up of what? 8 bits. Let's say 5, I'm organizing all the 4096 into 512 sets. So each set consists of 8 data bits. So I have to select one among the 512 column decoders required. Now again, the column decoder should require certain address. How much of address is required? So we know that 2 to the power of 10 is 1k. If I continue like that, 512k, that means a 2 to the power of, so 9, if I take 2 to the power of 9, it is a 2 to the power of 8 is 256, 2 to the power of, so one moment, so 2 to the power of 8 is 256, so 2 to the power of 9 is, so 512. That means that 9 address lines are required for this one. So totally 12 is required for selecting the row, 9 is required for selecting the column. So totally how many required? 12 plus 9. So 12 plus 9 means, so 21 address lines are required. So many times what will happen is, if the chip capacity is bigger, now I have taken a 16 megabyte. 16 megabyte is very less. Nowadays, you know that it's nothing but 256 megabyte, 512 megabyte will be like that when you design the computer memories. Number of address lines keeps on increasing. So to avoid this one, what they use, what is called as a concept called as address multiplexing is used. Address multiplexing is used. So what is the concept called address multiplexing? That means that I will be finding out among this row address and column which will take the more. Now in this case 12 is more than the 9. So I'll take only 12 address lines. So I am providing to the chip only the 12 address lines I'll provide. Even though 21 is required, I'll provide only 12. Now what I will do is, first I will send the row address. I will copy that in some place because why? I am using the same address lines to send column address later. So since I will be losing the address, I have to keep somewhere. So I'll be using a latch for that. We know that latch is the one which stores it. Since this latch stores an address, row address, it's called as a row address latch. Now this address bus is connected to the row address latch. Now how do I know that the data what is present on the address bus is belong to the row or column? So that is why we'll generate one signal called RAS. RAS means row address latch, row address select. So generally it's an active low signals. So I will place the row address, enable the row address signal, then the row address is copied, one particular row will be selected. Now same address bus now I'll be using to generate what is called as column address also. How much is a column address? 9 bits are required to select one of the 512. Again, we have to store that address. So that is why it's called as column address latch. Column address latch is available. So we generates this one. So now, what is an address multiplexing? The half of the address lines or the address lines which are required to select the row will be sufficient enough to send both the row address and column address. What is the way they do it? First, the part of the address, let's say row address 12 bits is sent and RAS is enabled. Then the same address bus is used to send what is called the 9 bits column address, and then again one signal is given called as column address select is given. Now column address comes here. So now you get what is the, after the you give us 9 bits, one of the 8 bits, that is one of the 512 sets of 8 bits will be selected and you get the data. So this concept is being used in almost all the DRAMs. Why this concept is used? Because the number of address pins are more. Concept called address multiplexing has been used. So since you have to generate RAS, CA signal you have to do, and you have to do what is called refreshing also. So every within 64 millisecond I have to refresh also. How do we do the refresh? So refresh is a concept. You don't require to perform a read and write. During refreshing, what we do, we generate a one pulse called as a read pulse. We do it. That means that it's nothing but a RA signal will be generated. When you generate a RA signal, all the cells present in a particular row will be enabled. If you just enable a row, it's good enough. The sense and write circuits which will identify what is the value present in a particular bit and refresh it. If it's a 1, it will recharge to 1. If it's 0, it will recharge to 0. That means that you need not to read it. You have to just enable RA signal and just access the complete row. If you just generate one pulse for the RAS, enable a row, it's good enough. It's called as a refreshing will happen. You have to just perform a read operation. You don't require to read the data also. Just generate a RAS signal. So these pulses has to be sent to all the rows. That means that every row have to select. So generate an RA signal, generate a row address. Again, increment the row address, increase, generate a RA signal. These pulses has to be given for every row so that all the data what is present in the row will get refreshed. So this is every once in a 64 milliseconds we have to do these operations. So this logic also to be done. So that means that the processor whatever you are used now, it is capable of generating what? One address. Let's say in this case 21 bit address it generates, and let's say the processor has got 8 bit data bus. Now the DRAM chip requires a different signals. What all the signals required? It requires RA signal, it requires a CA signal, it requires some refreshing circuit signal is required. Yes or no? All these are different, which is not present in the processor. That is why a memory controller, DRAM memory controllers are used. So what is the job of a DRAM memory controller? It takes the address, it takes the data will be connected directly to the DRAM. It takes the address, so it takes the read write the signals and all the control signal. It generates what all the signals required for the DRAM. So this type of memory controllers are required between the DRAM and the processor to generate RA signal, CA signal and the refreshing circuit signals. So that is why there is an extra circuitry what is required in the DRAMs, what is called DRAM memory controllers. So the next 5 minutes I just close with a other one. Now now we have other types of memory. That is a memory which is available in the DRAM is called a synchronous DRAM. Synchronous DRAM. So what is a synchronous DRAM? So synchronous DRAM is completely different from a normal asynchronous DRAM. So the one of the advantage of synchronous DRAM is it supports it supports it supports the word transfer and also the block transfer or a page transfer, the page transfer. So it has got a circuit capability of transferring one word or one block. Whenever you transfer one block or a page, you just give one row address sufficient. You don't require to give a column address. It will be generated inside automatically. All the subsequent words you can able to read it. That means that the first word reading may take 5 clock cycle, but all the subsequent words will require only 1 clock cycle. So there's a lot of advantage when you use a synchronous DRAM for a block data transfer. It has it has it has internal controller. It has an internal controller which generates all the RAs, CAS and the refresh signals, or it will generate inside. And this work in synchronization with the with CPU clock. That in the sense, whereas in the previous case a separate memory controller was required, it was not in sync with the CPU clock. It will take its own timings to generate, and the CPU has to wait till the complete access is completed. In case of synchronous DRAMs receives the clock from the CPU, and based on the clock, all the activities are synchronized inside in that one, including the refreshing. So that's the advantage of the synchronous DRAM. It supports all these operations. Now, let's see that how one synchronous DRAM is designed and how the signals will be generated. So it is also has got, I will, a general block diagram. I'll write it instead of taking a particular case of particular size. Say it contains a cell array. So similarly, it has got the cell array consists of number of rows and the column. So row decoder is required to select one of the rows of this one. Similarly, in a given row, you have to select a particular set of columns, that is a particular bytes or words you have to select among the many set of words present in a given row. So that is why we call as a column decoder. Like a previous case, it is also required. So, and these cell array along with the what is called as read and write circuit, there is a sense and the write circuit. It consists of one more component which is not present there in asynchronous DRAMs, is what is called as latches. So what is an advantage of a latches? It is used in a block transfer. I'll explain this one after completing these operations. Now it contains sense and write circuit along with the latches. Now, so since address is multiplexed like in asynchronous DRAM, we require row address latch is required, which generates the row address. Similarly, to generate the column address, to hold the column address latch is present. So, which contains this one. Now, both row and the column address are multiplexed. So, the same bus is used. The same bus is used to generate the row and column address. And it also has built-in refresh counter is there. The refresh circuitry inside the refresh counter is there. So this is capable of generating the pulses, refresh pulses within a 64 milliseconds, so that it will be refreshed. So the data whatever present inside the array will come out with the help of a buffer register. Two buffer registers available. We call as a data input buffer register. Whenever we want to write the data, so it's a data output buffer register will be available. So both are connected here. So similarly, I can write into this one, I can read from this one, and this is connected to here. This is the data what is present here. One speciality of this one, I said a controller is inbuilt into the synchronous RAM. So this controller has got what is called as a mode register, where I can select different modes of operation, word transfer, block transfer, page transfer, like that I can able to configure it. And this is capable of generating all the timing signals like RAS, CAS, all the signals will be generated by this one. So the processor gets interface to this one. The processor gets to interface to this one. Now, so these timing and all the signals what is required for this will be managed inside the chip itself. So this type of arrangement what has been provided in the synchronous DRAMs. So the only thing is in synchronous DRAMs are capable of block transfer. So there's a concept called latches is there. That means that if I select a one row, each row consists of number of the bits will be there. So these bits are grouped into words. So multiple words there in a one row. Now let's say a one row consists of 512 words are available. I want to read a block of data. Then generally what we do, first we generate an RAA signal, generate a row address, then select a column address, then read a one word. So for every word we have to generate RAS, row address, column address, we do it. In block transfer, what we do, we generate one row address, and then we know that many number of words are stored in a particular row. We will keep on reading one word after the other word without regenerating the row address. I have to generate only column address. So that is why. So this column address latch is also contains a counter also. Column address latch plus counter. They call it a column address counter. So this column address counter will keep on generating the next column. So first word I'll read it. second word, third word, fourth word, up to 512 words I can read it without regenerating the row address. So column address slash now act as a column address counter. The row address is not changed, row address is same. The different words present in a particular row will be read one after the other. It will comes like this. If you observe this one, if you observe in a clock cycles like this, let's say I require one clock cycle I require one clock cycle for applying the RAs. Let's say I'll apply the RA signal. So RA signal is nothing but what? It's an active low. I'll apply one RA signal. As soon as the RA signal is applied, I have to apply an address for that. So row address I have to generate. So now I will generate an address. So row address, let's say it requires 1, 2, 3 clock cycles. The row address will be there here. So this contains the row address. Now, after the 3 clock cycles, then CAS will be generated because 3 clock cycles are required for the row to be properly selected. So then it will generate one CAS signal for the one more clock cycles. Then after that, so we will be generating what is called as the column address. So immediately what will happen? Now for the one clock cycle, the column address will be placed, the row address which is being available here, which is being generated when the RAS is there, that it carries the row address. Then after that it will be empty. Then wherever the CAS is generated, so we generate the column address, it will be there. Then after that it will take one clock cycle for the column to respond. Then after that, the data whatever available which comes here, so that I'll get one data, that is a first word, let's say first word D0 word, I'll be getting it. Now how many? One clock cycle, 1 2 3, 3 clock cycle. Again for the column it will take one address, let's say one clock cycle, 4 clock cycle, 5 clock cycle, 3 4 5. That means that after the 5 clock cycles, or 6 clock cycles, in this case I have taken 3, I have taken 1 and the column address 1, and again one more, I given the gap, one more, 3 4 5 6. So I'll get a one data. Next one I have to generate it. I don't require to generate anything else, because why? Automatically the column counter will able to generate. I don't require even a pulses also. Column address counter will generate the next address. You'll be getting the next data. So like this, for every clock cycle you're going to get now one data, you're going to get D0, D1, D2, like this. So this is an advantage of a block transfer. In a block transfer, for first word of data transfer, you require multiple clock cycle. You may require 5 to 6 clock cycles are required. First apply the RAs, keep the row address on the data on the address bus, then generate CAS, keep the column address on the address bus, then give one clock cycle for the data to come. Then after that, all the further words will be keep coming for every clock cycles. So what is the bandwidth if I ask? The bandwidth will be very high. The more the block size, the bandwidth will be very higher rate, because these 6 clock cycles are required only in the beginning word. So like this, synchronous DRAMs are very popular in the market because it supports both the word transfer and the data transfer. So these synchronous DRAMs, so now it's available with a technology called DDR. So when I say DDR, SDRAMs means, normally as we have seen in the previous block diagram, one clock cycle means one positive edge. That means that every time an edge happens, you get a one word of data, you are going to get it. That is one data, one word you are going to get it. Whereas in case of a DDRAM, the technology has been completely improved. The concept of memory interleaving, the two banks has been arranged such that, so every edge is counted. The positive edge is also useful, the negative edge is also useful. In the positive edge, you get one word of data, you are going to get it. In the negative edge, you are going to get another word, you are going to read it. That means that, so the bandwidth become double. That means that, that's why it's called double data rate SDRAMs. So you read one word here and you read another one word here. To make this possible, they use a memory interleaving concept. So that is why double data rate SDRAMs are more popular. That is what used in a nowadays PC computers. So in a nowadays laptops and everything, they use DDR SDRAMs. These DDR SDRAMs are available as memory modules. So generally they are arranged in configuration. So these configurations will be, so generally in different capacities will be there. For example, so they are available as 4 megabit into 32, 16 megabit into 32, different capacities available. So 32M into 32 bit, different capacities memory modules are available. So these memory modules Each memory module consists of so many number of memory chips. Each can be contributing 1 bit, 4 bit or 16 bit like that. So if you are going for the larger size, that is they call as a what is called the two types of memory modules are called as, one is single inline memory module, other is called as dual inline memory modules are there. So the capacity of this is this range, whereas the dual in memory module capacities are little higher, 80 into 64. They use it for, so 16M into 64, like this capacities are available in the DIMM modules. So these SIMs or DIMMs are very commonly used in the computers to build the larger DRAM memory. So these are the types of DRAMs are used to realize the memories inside the computer. The cache what is present inside the computer are generally built using the SRAMs are available. So this is about how the different memories can be built using the computer.